Righty, g'day students, welcome to the lesson. Today we're going to look at the electronic structure of the atom. So that is, what about the electrons? So what we need to do is think about where the electrons are sitting in the atom. So we've learnt about the protons and the neutrons and isotopes so far. Now let's consider about the third subatomic particle. So the goal for today's lesson is going to look at the relative energies of the different locations where they sit. We call them orbitals. So we've got the S, P, and D. We've also got the F electron orbital as well. We can talk about that briefly. Talk about the Aufbau principle. That's just German for building up. Hund's rule and the Pauli exclusion principle to write electron configurations for atoms and ions that up to the 36 atomic number. You can see where that is on your periodic table. Okay, then we're going to determine the full and condensed electron configurations for atoms up to 36. I'm going to write them in full. For example, 1s2, 2s2, 2p6, 3s2, 3p5, and we can write them in the condensed form just by using the nearest noble gas configuration. We put that in square brackets. Then we're going to look at two exceptions to the electron configuration rule. Or exceptions to Aufbau principle, I suppose. Okay, so what do we know so far? We've talked about the Dalton model and then the plum pudding model from J.J. Thomson, and then we've worked out, okay, Rutherford shot alpha particles through gold foil, and most of the alpha particles went through, so most of the atom is just empty space. Then we came across Niels Bohr, and that's what we teach you up until year 10. And it's quite relevant still because atoms still sit at distinct energy levels. But then we're going to start to discuss the quantum mechanical model today, and that's normally just describes about the electronic behavior or the behavior of electrons and atoms. So it determines the allowed energies an electron can have and how likely it is to find an electron in various locations around the nucleus. That's where the shapes of the orbitals come in. So remember Niels Bohr, he pictured electrons like planets orbiting the sun, so electrons orbiting the nucleus, and he used that as an analogy. And this is really important. This is going to help us understand the principal quantum number. So that's the probable distance that the electron is from the nucleus. And we're going to call that m. So we just say the number of electrons that fit in the shell is 2n squared, and there's up to 7 energy levels. You see that aligns nicely with the periodic table, that there are 7 rows or periods in the periodic table. So if I look at this, we need to state there are 2 in the first, 8 in the second, 18 in the third, and 32 in the fourth period, or the fourth energy levels. So the first energy level can fit 2, the second can fit 8, the third can fit 18, and the fourth can fit 32. It's just 2 times n squared. So 2 times 1 squared is 2, 2 times 2 squared is 8, 2 times 3 squared is 18, 2 times 4 squared is 32, and so on. So the electron can sit in a variety of locations around the nucleus, and you can see that they take on different shapes, and we're going to discuss this a little bit further. You can see that S block generally sit in spheres around the nucleus, and you can see that I've got a 1s and then a 2s, for example, and you can see here's the 1s hiding inside the 2s, and then I've got 3 levels, so 3 spheres. But if I move over to here, I can also note that these are dumbbell shaped. So if I've got stuff in here, I'll have, no, let's go to this one. I have little dumbbells inside of here as well. And then we've got double dumbbells and a dumbbell and a donut, essentially. And then it just gets funky in the F block. So these orbital shapes are defined as the surface that contains the 90% of the total electron probability. That's where we're most likely to find them. Now, when you look at the periodic table, it it's arranged according to how the electrons fill up. So we stopped teaching you after calcium in year 10 because that's when we get a little bit of confusion, and that's these guys here. So calcium is your 4s2 electron. So we teach it up to this level, and you can see here that the 3D electrons fill in after the fourth energy level. So the fourth energy level is a lower energy than the 3D level. So we've got the lowest energy to the highest energy. So the Aufbau principle is just the filling up. That's what it is in German. So Aufbau principle states that for atoms in their lowest energy states, electrons got to fill up down here first in the lower energy subshells before progressively filling up in the higher ones. And the pattern goes like this. There's 1s, yeah, then 2s, then 2p, 3s, 3p, then you can see there's 4s. And there's a little tip to do this now. So what we do is we just write down the left-hand side 1s, 2s, 3s, etc. And then next to that, we just write 2p, 3p, etc. And then 3d, 4d, etc. And then 4f and 5f. And you can see then we just do it on an angle to determine the order of filling. When we then determine the order of filling, we can then write the electron configuration according to the Aufbau principle. So we've got the coefficients, so that's the energy level. And for example, I might have 2 electrons in the first energy level. You can see that there's 2 atoms on the first row of the periodic table, for example. Then I've got 2s, so I fill in then 1s, then 2s, 2 in that second one. So the S is the subshell being filled. Then I fill in 2p. I can fit 6 along here. So I go up to a maximum of 6. And then once my 2p are filled, then I go to the 3s one. So the energy level of 4s is below that of 3d. So this is the tricky bit here. This is another way to visualize it. It just means that that 4s subshell will fill before the 3d. And so that just means when we're writing it out, we just got to remember that. So let's have a look at krypton. So the objective is that we've got to do up to krypton. So let's write the electron configuration of krypton. So we just write this out on a bit of paper if we need to. So we go, well, 1s2, then 2s2, then I read across to 2p6, and then I read down to 3s2. Okay, after 3s2 is 3p6, then I go to 4s2, and then I can go, what's 4s2? 3d10, and then 4p6. So the electron configuration for krypton is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. When we're calculating this, you'll notice that sometimes, for example, I'll write 3d10 after 4s2 when I'm doing my Aufbau principle, but when I'm finishing off, I'll just put them into the appropriate energy levels. And then you can see, okay, I've got 10 plus 6 plus 2. I do have 18 electrons on my third energy level, and that's what's particularly confusing for year 10 science. So that's why we stopped there. Now, there are 2 exceptions to the Aufbau principle, and that's copper. Here we go, copper and chrome. And you can see that, okay, so that's a 3D4 and that's a 3D9. So there's something that's going to happen here. Instead of filling up the 4s subshell, these filled energy subshells are just going to be more stable than the partially filled subshells. So by Aufbau, we predicted copper, for example, to be what? 1s2, 2s2, then we've got 2p6, 3s2, 3p6. Then we predict it to be 3d9, 4s2. That's what we predict. But what's going to happen is it's going to actually fill this subshell before filling up the 4s1. So that's an exception to the Aufbau principle. And the same thing with chrome. It's just going to go 3d5 4s1. Now, with electron configuration, I can write that in condensed form, and I just go to the nearest noble gas. For example, if I'm writing sodium, it's number 11. I can write 1s2, 2s2, 2p6, 3s1. Now, if I look at the nearest noble gas, that's neon, and you can see that that's got the same electron configuration as that. So just a shortcut is to write the nearest noble gas in square brackets, and then the next energy level. And you can see some more examples up here. So that's Aufbau. Hund's rule tells us that electrons fill a subshell singly before forming any pairs. And we'll talk about that with Pauli as well. So essentially we're going to fill up 1s2, 2s2, and then 3p1, 3p2, 3p3, then, 1s2, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, and they're going to spin down. That's Pauli. So electrons occupy singly before pairing. So if I have a look at this, we're filling up. Oh, well, let's read this out. When electrons occupy orbitals of equal energy, so the 2p, for example, each electron enters the orbital until all the orbitals contain one electron with parallel spins. And you can see what's happening here. As I go along the periodic table, I'm just filling up electron shells singly. Then I come to oxygen, and you can see that, okay, this 2p4 is actually spinning the other way. And then here's the 2p5 and then 2p6. So Pauli is interesting. He's saying, well, you can only have 2 electrons per orbital, and the paired electrons must have the opposite spins. That's why we're never going to have 3 electrons in one box. And just remember, electrons are negatively charged, so like charges repel. So that's the best way to think about it. And so if you've got one spinning one way, the other one's going to spin the other way. In fact, there's going to be a little bit of propulsion. It's going to be easy to pull this one off. So this has got a pretty low ionization energy. And we'll get to that in periodic trends next lesson or the one after. Finally, let's just think about the orbital shapes. The orbital shapes are the regions within an energy level where there's a probability of finding the electron. And that's got to be generally to about 90% probability. Now, the s orbital has a spherical shape, which you saw on that GIF earlier in the slideshow. And it's also a 3-dimensional thing. So remember, Bohr had the 2-dimensional model, and with quantum mechanical model, we are thinking 3-dimensional. Now, the p orbital, you've got an x, y, and z axis. So think about a graph. In years like 7 to 10, you've done graphs with x and y axes. Now we've got another one for height, depth, and width, for example. So we're going to fill up this one, then fill up one of these, fill up one of these, then fill up one of these, fill up one of these, and fill up one of these with the electrons. P orbitals, as I said, now you don't really need to worry too much about the shapes. You just go, this is kind of interesting that this is where we're going to find electrons. So I think of them as a double dumbbell, for example, here, double dumbbells, and this one's got a dumbbell and a donut. So they're 5, because what do we got? We got 10 electrons in the D block. So we've got to have 5 orbitals and have 2 electrons per orbital. And then finally with the F block. Now, F blocks are kind of interesting. They sit underneath the D orbitals in terms of energy, and they do matter because they do give us some influence on things like magnetism and color in metals. And that's pretty well as complex as we need to get. You don't need to remember this at all, but it's kind of interesting. So finally, just to recall what we've done, we've stated the relative energies of the S, P, and D, so lowest, middle, and highest. We're only doing up to krypton, so we don't need to worry about F. but F is higher. Apply the AFBAL, so it's a filling up, the Hund's rule and the Pauli exclusion principle to write down electron configurations of atoms and ions. Now, look, the ions are just going to have different number of electrons. So, for example, non-metals will gain electrons and metals will lose electrons when they form ions. Going to determine the full and condensed electron configurations for Z to 36, so that's krypton, and want to write it in full electron configuration as well as condensed. And then we finally identified the exceptions to the AFBAL principle, which are chrome and copper, and explained that.